EE5508 Semiconductor Fundamentals. Lecture 3 Band Gap Engineering, Heterojunctions, and Quantum Well. Section 3.1 Semiconductor Alloy. By alloying semiconductor, it affects the energy band structure and band gap. Lattice parameters, for example, lattice constant, mechanical constants, these include elastic moduli, defects, formation energy, etc., as well as optical and electronic properties, and also many other aspects of the resulting material, such as scattering rate. For example, your mobility is Q tau over M. Tau is your scattering time, so it affects the scattering rate. Now, it's very difficult to grow bulk single crystal compound semiconductor or alloy with adequately controlled chemistry. For example, submicron size devices, the grain boundaries and dislocations can have a profound effect on the electronic properties. So usually we would like to grow semiconductor alloys with single phase or a single crystal with nearly perfect mixing so that it can be useful for devices application. There are two common options for making high quality single crystals or single phase. Either you grow them as a bulk materials or you form them as a thin epitaxial single crystals on a large single crystal substrate. The term epitaxial basically refers to align the lattice of one crystal in a specific way relative to another, such that a thin crystal is grown on a thick substrate with a well-defined lattice orientation. So the term epitaxy actually comes from the Greek roots, epi meaning above, and taxis meaning in ordered manner. So it can be translated to arrange upon. So we call this the epitaxial growth. So to obtain a good epitaxial layer, the lattice constant of the alloy should be very close to that of the substrate. So common semiconductor substrates include silicon, germanium, gallium arsenide, indium phosphide, aluminum oxide, or commonly called sapphire, silicon carbide. The more rare semiconductor substrates are the gallium antimonide, indium arsenide, cadmium telluride, and many more. Now let us look at how do we form semiconductor alloy. For binary 3-5 semiconductors, group 3 element and group 5 element for a periodic table. So usually we call this the binary 3-5 semiconductors or compound semiconductors. So you can have aluminum nitride, aluminum phosphide, aluminum arsenide, aluminum antimonide, or gallium nitride. So it should be Ga, gallium, gallium phosphide, gallium arsenide, gallium antimonide, or indium nitride, indium phosphide, indium arsenide, indium antimonide. Now, the other way to form 3-5 semiconductor alloy is to make use of 3 elements from the periodic table. So we call this the ternary 3-5 semiconductors. For example, 2 group 3 elements in the periodic table, aluminum and gallium, and 1 group 5, which is the arsenic. So you form aluminium gallium arsenide. And the way we write this is with X as a subscript on the aluminium, and then gallium will be minus X. So X is basically the fraction of gallium atoms in the gallium arsenide that are replaced by the aluminium atoms. So we call this the aluminium gallium arsenide. So, or sometimes we call it X as the compositional mixing ratio or mole fraction. Okay, it varies from 0 to 1, or we say from 0% to 100%. So if X is 0, there's no aluminium, then here 1 minus 0, you have only gallium arsenide as the compound semiconductor. If X equals to 1, then you do not have gallium, so 1 minus 1 is 0. So you have only aluminium arsenide as the compound semiconductors. So the X basically is a compositional mixing ratio ranging from 0 to 100%. So when we grow aluminium gallium arsenide, we grow in excess of arsenic, okay, by adjusting the aluminium and gallium ratio. You can also grow two group 5 element and one group 3 element. So you form gallium arsenide phosphide. Or you can even have quaternary 3,5 semiconductors, 4 elements from the periodic table. You can have 2 group 3 element and 2 group 5 element. So you form indium gallium arsenide phosphide. So again, recap that in the periodic table, this is your group 3 element, this is your group 5 element, this is your group 2b element, and this is your group 4 element, this is your group 6 element. So you can even have 2,6 semiconductor alloy. So for example, you can even have zinc cadmium oxide or zinc cadmium sulfide. Next, let us talk about lattice matching. Starting with a substrate, which is a semiconductor single crystal with a lattice constant A, S stands for the lattice constant of the substrate. And let's say if you grow a film, okay, deposited on top of the substrate, AF is the lattice constant of the film. And the lattice constant of film is larger than the lattice constant of the substrate. So in this case, there's a possibility that you can basically compress the film such that it will match the lattice constant of the substrate. So we call this a compressive strain layer structure. Okay. Or you can deposit film with a lattice constant of the film smaller than the lattice constant of the substrate. And then what you expect is the film itself will stretch laterally to match the lattice constant of the substrate. So if you stretch laterally, then vertically it will basically compressed. Similarly, for compressive strain, if compressed laterally, then vertically we will be stretched. So this is known as the tensile strain layer structure, where the lattice constant is stretched laterally. Now, whether the strain can be accommodated at the interface when you grow the film on the substrate very much depends on the critical layer thickness of the film that you can grow. This means that there is a certain layer thickness you can grow the film before the dislocation occur. So you can probably grow the film up to a certain layer and the strain can be accommodated at the interface such that the film and the substrate, the lattice constant, still can be matched. So lattice matching is basically the film is stretched or compressed such that its lattice constant matches that of the substrate, and the bond between the atoms of the lattice constant and the film lattice constant at the interface, the bonding is continuous. Now, lattice mismatch is when the film is either relaxed partially, such that the lattice constant of the film and substrate do not match. So if you deposit the film on the substrate and the lattice constant, let's say, does not match, and the strain, cannot accommodate, such a lattice matching, then we say the film is relaxed. The way we calculate the strain, is denoted as a symbol of epsilon, is substrate lattice constant minus the film lattice constant over the film lattice constant. So in this case, AS is smaller than AF. AS minus AF will give you a negative value, and we call this the compressive strain. If AS, in this case, the lattice constant is larger than the lattice constant of the film, then this is a positive value. So the strain is positive. We call this the tensile strain. Now, the strain is only allowed up to a particular thickness, which we call the critical layer thickness, such that it can be accommodated at the interface and the lattice constant of the film and the lattice constant of the substrate can still match. So what is this critical layer thickness? I will just quote the result. So in the material size, the critical layer thickness will be the lattice constant of the substrate divided by 2 epsilon. So this is a modular sign. So critical layer thickness will be always a positive value, and epsilon is defined as a strain. So if the critical layer thickness is exceeded, you expect defect to be generated. So for example, let's say I grow Indian gallium arsenide alloy on gallium arsenide substrate. The lattice constant of the Indian gallium arsenide is larger than the lattice constant of the gallium arsenide. So it's in this case, we expect to have a compressive strain layer structure. So this thin layer of Indian gallium arsenide can be grown on the gallium arsenide, and is basically stretched, or is compressed in the lateral direction. So you can see the bonding is continuous. Now, basically in this case, the strain itself, is basically conform the lattice constant of the gallium arsenide in the plane of the heterojunction, at the interface. Now, if you grow too thick of an Indian gallium arsenide, then the strain is relaxed. Basically, the film is relaxed. There's no longer strain. and you will introduce misfit dislocation at the interface. Okay, so sometimes we call this the hetero interface or just interface between the two dissimilar semiconductor. So for the two dissimilar semiconductors or two different type of materials, and the junction that is being formed at the interface, we call that a heterojunction, or the interface, we call that the hetero interface. Now, so we say the strain is relaxed, okay, or the strain relief, okay. Either can also occur by dislocation formation, which is in this case, it causes a mismatch and there's a misfit dislocation, or it can also, the strain can be relaxed, okay, by forming island without dislocation. So in this figure, for example, people have studied germanium, okay, having a lattice constant larger than silicon, which is about 4% difference or 4% mismatch, trying to grow germanium on silicon. So actually, the relaxation, there's a strain relaxation, but this relaxation does not induce dislocation. So the relaxation without dislocation formation actually has been studied extensively or modeled using linear elasticity theory. So basically the model have shown that for moderate misfit or moderate film thickness, the strain can be maintained in small island. Okay, so after you grow, it tends to form an island, okay, on the substrate, even well beyond the critical layer thickness that we have calculated in this equation. Okay, so the three-dimensional island, okay, actually relax the strain elastically, okay, without introduce any dislocation. And such a formation of 3D island growth, okay, was discovered by Strucky-Krastanov. So such a growth is called Strucky-Krastanov growth. Now, this is another picture, okay, a transmission electron microscopy picture showing indium arsenide, and we call this a nano island. It grown on gallium arsenide surface. Okay, and this was imaged by an atomic force microscopy. Okay, sometimes you also can observe by transmission electron microscopy. Okay, for example, I grow silicon on germanium, and then the germanium actually form the island. So basically, I go using a substrate, I go a germanium and form the island. The next layer, I grow silicon again, and then I grow germanium on top of it, I form an island. So I alternate between silicon, germanium, silicon, germanium. So the germanium island actually can be aligned on top of the underlying island. So and such an exotic material can be used in even optoelectronics devices. So in this case, such a flame of high misfit, okay, might lead to dislocation formation. They do not grow as a uniform thin layer, but they rather form an island on the substrate. Okay, let us look at the 3-5 semiconductor alloy more in depth. So A, B, C are the elements in the periodic table. So ternary alloy are 3 elements in the periodic table. You can have 2 group 3 and 1 group 5. So it's aluminum, gallium arsenide, So you grow in excess of arsenic, you basically control the mixing ratio of aluminum and gallium, where X is the compositional mixing ratio, and in this case is the fraction of gallium atoms in the gallium arsenide are replaced by the aluminum atoms. So 2 group 3 and 1 group 5. Similarly for indium gallium antimonide. Or you can grow 1 group 3 and 2 group 5. So for example, in this case, this is a gallium arsenide phosphide, or you can have aluminum arsenide antimonide. So you grow in excess of aluminum by controlling the arsenic and antimonide mixing ratio. For 4 elements, call them the quaternary alloy. So A, B, C, D are in the periodic table, and then you can control the X and Y composition. So you can have 2 group 3 and 2 group 5 elements. So aluminum and gallium, you control the ratio of the X of aluminum. Arsenic and phosphorus, you control the ratio of the arsenic. So when X equals to 0, you have only gallium arsenide phosphide, where you come back to a ternary alloy. So when X is 0, no aluminum. X is 0, you just have gallium. And then arsenide and phosphide, you did not change your Y, so it become a ternary alloy. You can also have aluminum indium arsenide antimonide, or you can have a 3 group 3 element, aluminum, gallium, indium, 3 group 3 element in the periodic table, and 1 group 5 element. So these are aluminum, gallium, indium, arsenide. Or you can have 1 group 3, which is indium, and then you have 3 group 5 element, arsenic, phosphide, and antimonide are 3 group 5 element. So do not worry too much about the position where we put the X and Y composition. Okay, as we go along, okay, whatever composition that we discuss, okay, X and Y will be positioned, okay, accordingly for our discussion. Next, Verga's law. Now, the lattice constant actually changes linearly with composition of the alloy, from that of one compound to that of the other. So, for example, in semiconductor, let's say you have a compound AB and another compound AC, where A, B, C are the element in the periodic table. Okay. And let's say compound A, B, and AC have the same crystal structure. So let's say gallium arsenide and aluminum arsenide have the same crystal structure, or gallium arsenide and gallium phosphide have the same zinc blende crystal structure. And then you form an alloy. Let's say gallium arsenide, gallium phosphide, 2 compound semiconductor, and you form an alloy called gallium arsenide phosphide. Okay, by adjusting the arsenic and the phosphorus ratio. We expect the final alloy also have the same crystalline structure. And in this case, as far as the lattice constant of the alloy is constant, you obey the Verga's law. And this Verga's law is basically just the average of the lattice constant of the pure compound weighted by the composition ratio. So if you have ABC, okay, that is your semiconductor alloy, then X, okay, on the B will be AB is your lattice constant plus 1 minus X down here, and AC is your lattice constant. So it will be clearer to show an example. What is the lattice constant of gallium arsenide phosphide alloy, given the following lattice constant of gallium arsenide and gallium phosphide? So gallium arsenide phosphide, okay, if you look at the endpoint semiconductor or the compound semiconductor from this alloy, is basically gallium arsenide and gallium phosphide. So basically the gallium arsenide, okay, the arsenic, okay, is some of the percentage, or in this case 40% of the arsenic in the gallium arsenide is replaced by the phosphor. So therefore you have gallium arsenide phosphide, so 0.6 on the arsenic and 0.4 on the phosphorus. So what is the lattice constant of the alloy? So it's basically 0.6, okay, of the lattice constant plus 0.4 of the gallium phosphide. Okay, so it will be written in this form to find the lattice constant of the alloy. So you can basically deduce the lattice constant of the alloy from the original compound semiconductors. So gallium arsenide phosphide is basically made up of gallium arsenide and gallium phosphide. And most of the mechanical property are also shifted linearly with alloy composition. And mechanical property are determined by substantial volume of the semiconductor crystal. So any local composition fluctuation, okay, are basically averaged out and do not affect the property at all. But however, in terms of optical electronic properties, sometimes it's important because some of these optical electronic properties are determined by very small volume. So they may not scale simply with composition. So therefore, the lattice constant cannot be approximated by Verga's law. So Verga's law is just none other than a linear approximation, okay? An average of the lattice constant of the compound weighted by the composition. Okay, next, we look at how the band gap changes, okay, for the alloy, or we call it the band gap engineering. So again, the materials parameters, either the lattice constant or the band gap of the semiconductor, are normally derived from those of the endpoint compound in terms of a simple interpolation procedure called the virtual crystal approximation. So this is none other than a linear interpolation or linear approximation. So the gallium arsenide phosphide, the endpoint compound semiconductor, is basically gallium arsenide and gallium phosphide. So virtual crystal approximation assumes the material is nearly perfect random alloy. So you mix, let's say in gallium arsenide phosphide, the arsenide and phosphide mix very well, okay, in terms of its mixing ratio. And the electronic structure can be obtained from suitably average the parameter of the constituent compound. The constituent compound will be your gallium arsenide and gallium phosphide. So in other words, gallium arsenide alloy, a lattice constant, the band gap structure can be obtained by taking a weighted average from the endpoint compound semiconductors. So the band gap as a function of ABC, the alloy, okay, is basically again X times AC of the compound semiconductor plus 1 minus X BC, the compound semiconductors. So basically, if this is gallium arsenide phosphide, so again, X times the band gap of gallium phosphide plus 1 minus X, okay, of the, this is aluminum gallium arsenide. So you grow in excess of arsenic. So AC will be aluminum arsenide. BC will be gallium arsenide. So X times the band gap of aluminum arsenide plus 1 minus X times the gallium arsenide. So you get the band gap, the alloy. Similarly, if you just change the band gap, okay, to lattice constant, you will get the linear approximation again. And we called that previously the Vergat's law. Okay, so both are basically linear approximation. It's just that they use the word Vergat's law for the linear approximation of the lattice constant and virtual crystal approximation for the linear approximation of the band gap of the alloy. Now, in some cases, okay, the band gap itself does not, okay, vary linearly because this is a linear equation. And there's a Boeing effect arises from the disordering in the semiconductor. Disordering can be due to lattice defect or even impurity, okay? And therefore, one usually defines the band gap become a second order polynomial equation. So X times band gap of aluminum arsenide plus 1 minus X times gallium arsenide minus B X bracket 1 minus X. This is the usual way, okay, we write the band gap equation if there is a Boeing factor. So the first part is the same, except that you introduce a minus bx bracket 1 minus x, where b is a Boeing effect, or sometimes we call that the Boeing parameter. It can be a negative or positive value. Okay, it's a numerical value. So if you look at this equation, the band gap grows like a x squared dependence of the composition. This is a linear dependence. And that, okay, tells you down here if it's a polynomial dependence of degree 2, okay, there is some disordering in the semiconductors. Now, Boeing itself, okay, this word Boeing is due to the disordering in the semiconductor and is also linked with the miscibility, okay. Alloy with large Boeing will have a large region of phase separation. So one may expect poor miscibility in alloy with large Boeing. Now, you may have encountered miscibility, this word in the material science course. So miscibility is the property of the substance to mix in all proportion. So if we say the material is, these two material is miscible, that means it's able to fully dissolve in each other at any concentration, and they form a homogeneous solution. Okay, substance do not mix are said to be immiscible. So for example, you try to mix water and oil, okay, these are substances immiscible. And then you will have a miscibility gap, which we will discuss more in detail later on, with a region in the phase diagram that you have a component where the mixture exists as two or more phases. So for example, you try to grow boron gallium nitride. Okay, basically the gallium nitride is alloyed with boron. But boron and gallium nitride itself have about 20% lattice mismatch. So you tend to have a lot of strain at the interface. And this basically will drive the alloy, like for example, growing boron gallium nitride into phase separation. So you may end up, okay, with some portion in the semiconductor having boron nitride or having gallium nitride cluster. So high quality boron gallium nitride cannot exceed 2%. Okay. Basically, the boron itself, okay, at most you can grow is 2%. If you try to grow more than that, then by changing the composition, you are growing greater or more boron, changing the lattice constant of the alloy, and this will induce strain, and strain will drive dislocation. And such a dislocation sometimes may also cause phase separation. So in boron gallium nitride, sometimes you will cause some clustering of boron nitride and some cluster of gallium nitride. So it does not form homogeneous, okay, boron gallium nitride alloy. So therefore, you will produce a miscibility gap in the phase diagram where exists two phases, boron nitride and gallium nitride phase. And then this will result, okay, in the band gap, okay. Instead of having a linear dependent on the composition, it will depends on you will have a square dependence. And this can, okay, be governed by a Boeing factor. Okay, so your band gap will be goes like a quadratic dependence. Now let us look at more example. What is the band gap of gallium arsenide phosphide alloy without the effect of Boeing factor? That means there's no disordering in the semiconductors. No. So gallium arsenide phosphide is formed from gallium arsenide and gallium phosphide endpoint semiconductors. So the band gap of gallium arsenide is given at 1.424 eV. Band gap of gallium phosphide is 2.75. So to find the alloy, you just use linear interpolation, or we call it the virtual crystal approximation. The arsenic is 60%. So gallium arsenide will be 0.6 times the band gap of gallium arsenide plus, okay, phosphorus 40%, okay, being replaced, or phosphorus replacing arsenic, okay, with 40% of the phosphorus. So gallium phosphide, okay, 1 minus X is actually 0.4 times the band gap of gallium phosphide. That gives you the band gap of the alloy at 1.954 eV. Example 2, what is given the band gap variation of gallium arsenide phosphide as a function of the composition is as follows. That means I give you the band gap energy as a function of composition to be of this form. If you look at this equation itself, it makes a comparison. Okay, the factor in front of the x squared is b, so that is your Boeing factor. So what is the value of the Boeing factor? Actually, is 0.176. What is the band gap of the gallium arsenide phosphide? Okay, with arsenic 0.6, phosphorus 0.4. Okay, 40% of the arsenic is replaced by phosphorus. So basically, you need to plug into this equation, and you need to plug in the x value. Now this equation, okay, basically tell you the x itself is on the phosphorus. So the phosphorus itself is 0.4. So you have to plug in the 0.4 value into this equation instead of 0.6. Okay. And then you get 1.912. That is your band gap, okay, due to disordering, okay, and it's lower than the band gap of this without the Boeing effect or without disordering. Now, what is the lattice constant? Okay, using the Boeing factor that I obtained in A, the Boeing factor is 0.176. So again, if you go back to this equation is in terms is for the band gap, but it's a linear, it's a second order or quadratic equation. So simply you basically just replace the band gap, okay, for the lattice constant. You also can calculate the lattice constant, okay, of the alloy due to disordering. So you have your equation of gallium arsenide phosphide. Okay. If you go by this equation, Bx squared plus, this will be your gallium phosphide plus A gallium arsenide minus B X plus A gallium arsenide. And you just plug in the lattice constant value of the gallium phosphide and the gallium arsenide. You'll be able to get the lattice constant of the alloy of gallium arsenide phosphide, okay, to be of this value. Next, effective mass. Lattice constant parameters, band gap parameters, okay, can be approximated by linear interpolation. The effective mass also can be approximated by linear interpolation. So the effective mass, okay, of course, by the same analogy, you can have x ma plus 1 minus x mb, okay, asterisk. There's a mistake, forget about the n here, okay. So, but in literature, usually we take the inverse value, okay, of the alloy. So it's 1 over m naught, m star alloy effective mass plus x bracket 1 minus ma plus 1 minus x bracket 1 over mb star, where a and b, ma and mb are the effective mass, okay, of the compound semiconductors. So for example, what is the electron effective mass of gallium arsenide phosphide using the virtual crystal approximation? Now, given the electron effective mass of gallium arsenide to be 0.067 m naught, and effective mass of gallium phosphide to be 0.2 m naught, where m naught is a free electron mass. So by using this equation, you can calculate the gallium arsenide effective mass, okay, 0.4 bracket times 1 over the effective mass of gallium phosphide plus 0.6 times 1 over the effective mass of gallium arsenide. And by plugging in the value of gallium phosphide and gallium arsenide effective mass, you can calculate the effective mass of gallium arsenide phosphide alloy. So there's no reason why we can't use this, but okay, we go by the standard literature. Okay, we use a weighted average by taking the inverse of the effective mass of the alloy. And of course, the carrier mobility, remember, is related to the effective mass. So mobility is equals to Q tau over M. Okay. So the mobility of the free carrier is determined by the effectiveness of the material. So when we make an alloy, we also modify, okay, the effective mass. Next, let us discuss the band gap of the alloy, okay, in more details. Now, let's take the example of aluminum gallium arsenide. Now, a makeup of the endpoint semiconductor of aluminum arsenide and gallium arsenide. Aluminum arsenide and gallium arsenide are both zinc blende semiconductors. However, aluminum arsenide is an indirect band gap. Gallium arsenide is a direct band gap semiconductors. So, if you change your composition, okay, there will be a point, okay, where there is a change from a direct to indirect band gap for a certain composition. So this is a plot of the energy gap or band gap as a function of composition. So when X equals 0, there's no aluminum, so you have only gallium arsenide. So this is the endpoint semiconductor, which is a gallium arsenide. If X equals to 1, basically is basically aluminum arsenide alone. So X equals to 1, this is the other endpoint of the semiconductor. So as you slowly change the composition by replacing the gallium with aluminum of certain composition, there will be a point where at a certain composition, the gallium arsenide will change from direct band gap to indirect band gap. Because gallium arsenide is a direct gap, aluminum arsenide is an indirect gap. So by keep replacing gallium with aluminum, there will be a composition, a certain composition that aluminum gallium arsenide become a indirect band gap. Okay. So let us look at this band diagram. The red curve is known as the gamma line. So the gamma line is an energy gap and is defined as a measure from the bottom of the conduction band at the gamma point with respect to the top of the valence band at the gamma point. So this line, okay, represent the energy gap, okay, measure from the bottom of the conduction band to the top of the valence band, both at gamma point. So there's a representation of equation here. E gamma dash gamma. Okay, so the first gamma is referred to the top of valence band. The second gamma refers to the bottom of the conduction band. So both bottom conduction band and the top of valence band occur at the same K point, which is the gamma point. And for x less than 0.45, the x less than 0.45. So from here to here, this curve can be represented by this equation, which is a straight line. Beyond 0.45, it tends to go like a square dependence. Now, for x line, it's basically measuring from the bottom of the conduction band at the x value to the top of the valence band at the gamma value. So the gamma value at the top of valence band always taken as a reference point. So again, this value, as you change the x, you will be able, this gap will also changes. So this is the x value, the energy gap of the x value respect to the top of valence band. So we represent it as gamma dash x. Okay, again, first gamma refer to the top of the valence band, and the second symbol x is referred to the bottom of the conduction band, and is represented by a quadratic equation to the x squared. So it can be fitted by X squared dependent. Next is the green curve, which is the L value. So again, okay, here the bottom conduction band at the L value respect to the top of the valence band, okay, that represent the value of this green curve. So as you change the composition, this gap, okay, or you measure vertically downwards from the top of valence band, the gap changes. So gamma dash L, first symbol, top of valence band, L, the bottom conduction band at the L value, is represented by a quadratic equation. So right at x equals to 0, we can see that gallium arsenide is a direct band gap semiconductor. Okay, so both are bottom of the conduction band, but this is the minimum, and they occur at the same point as the top of the valence band gamma point. So this is a direct gap semiconductor. And this gap, the value is around 1.41 eV or 1.24 eV. Okay, 1.24 eV. The next gap will be the L. So measure from here downwards the top valence band. That gives you 1.708. And the highest one, okay, will be this gap, which is the X, 1.9. So measure from here to here, 1.9. So as you change the composition, the gamma at the conduction band, the L at the L value, and the X, okay, at the X, the conduction band at the X value, the conduction band at the gamma value, the L at the conduction band at the L value will change, okay, with respect to the top valence band as you change the composition. So basically, you can see that at certain composition, okay, gamma and X meet at a certain point. So this point is basically the crossover point, which means that the gamma, the conduction band at the gamma point and the conduction band and the X value both have the same value with respect to the top of valence band. And that occur at X equals to 0.45. Okay, beyond X 0.45, you can see that the energy of the X value respect to top valence band is lower compared to the one with the red curve, which is a conduction band respect to the top valence band. So it's actually become an indirect band gap semiconductor, which is in this case, because after hit the crossover, the X value is the minimum value with respect to the top of the valence band. So this is the indirect band gap, okay, of the semiconductor. As it goes to X goes to 1, become an aluminum arsenide. So again, this is the indirect gap of 2.16 eV. So from here to here is 2.16. And then the next one, which is the red one, which is the highest. So the red is higher, bottom of conduction band of the gamma value is higher than the bottom conduction band at the L value. So this is 3.018. Okay. So you can see that when we replace gallium with aluminum to form aluminum gallium arsenide alloy, and starting with gallium arsenide is a direct band gap. Aluminum arsenide is an indirect band gap. As your composition increases, there will be a point where the alloy will change from a direct band gap to an indirect band gap semiconductor. So for light emitting diode, if you want to use aluminum gallium arsenide, you will wish to use the composition below X 0.5. So within this part, this will be a direct band gap semiconductor. So you can see that gallium arsenide 1.424 EV is in the infrared wavelength. Let's say you put about 30%, which is still a direct band gap. So the gap value is a direct band gap value is about 1.8. That goes into the ray. So by replacing gallium, some part of the gallium with aluminum before aluminum gallium arsenide alloy, you can change the wavelength from infrared to red wavelength. Let us look at another example. Indium gallium arsenide alloy. So it formed from the endpoint compound of indium arsenide and gallium arsenide. This is a band gap as a function of composition. So at x equals to 0, okay, x equals 0, you have indium arsenide. So it will be this point. Of course, you can flip over to put x equals 0 here and 1 here. It doesn't matter. So let's say x equals 0 here, indium arsenide, and x goes to 1, you have gallium arsenide at this point. So you change from the composition, slowly change from 0 to 1. And you look at the band gap energy. So the red curve, this arrow point to this axis, which is the band gap energy. So this is measured from the top of valence band for each curve. So this is the bottom conduction band, okay, measured from the top of valence band. The green one is again bottom conduction band L value respect to the top of valence band. This again the gap from the bottom conduction band at the X value respect to the top of valence band. So the gamma point for the conduction band respect to the top of the valence band is always the lowest. So it's always a direct band gap semiconductor. So because indium arsenide is a direct band gap, gallium arsenide is a direct band gap. So intuitively, you expect as you change the composition, it will still remain as a direct band gap for all composition of X. Now this curve is basically the effective mass, okay, M star over M naught. So as you change your composition for X equals 0 to X equals 1, the effective mass will change. So what is using Virga's law, what is the lattice constant of indium gallium arsenide? You can calculate that, okay, for a composition of indium of 53%, gallium 47%. So 0.53 plus 0.47 add up must be 1. So you can use linear approximation to obtain your lattice constant of 5.8680, which is very close to the lattice constant of indium phosphide, which means that you can grow indium gallium arsenide alloy on indium phosphide substrate. Next, let us look at one example. Okay, how do we use virtual crystal approximation to calculate the semiconductor quaternary alloy material of indium gallium arsenide phosphide? Before we do that, let us look at one of these classic graph or the plot of band gap as a function of lattice constant. Okay, band gap as a function of lattice constant, not band gap as a function of composition. Band gap as a lattice constant. This right axis is the wavelength. So the band gap is in measured EV. Of course, you can convert to wavelength because 1 EV will give you 1.24 micron. So this is measured in micron. So these are the point of the binary semiconductor. So basically, your gallium phosphide will have this band gap value of around 2.3 EV, or you have gallium arsenide of 1.43 EV. And let's say if I want to grow gallium arsenide, indium gallium arsenide phosphide. Remember indium gallium arsenide phosphide. The endpoint of the semiconductor is indium phosphide, gallium phosphide, gallium arsenide, gallium phosphide. These are the 4 endpoint semiconductor of the indium gallium arsenide. Okay, you don't have indium gallium, which is not a semiconductor, or you cannot have arsenide phosphide, which is 2 group 5. They are not semiconductors. So there's only 4 possibility. Okay, indium arsenide, indium phosphide, gallium arsenide, gallium phosphide. So these are the endpoint semiconductors. So the gallium phosphide, gallium arsenide, indium arsenide, indium phosphide. These are the 4 endpoint binary semiconductors. Okay. So if I join these 4 points together, okay, basically we are saying that the gallium arsenide, okay, this line to the indium arsenide, this is the ternary boundary line of the indium gallium arsenide. Because this is gallium arsenide, this is indium arsenide. So this, okay, line is the indium gallium arsenide boundary line. And this line is indium arsenide phosphide boundary line. This indium phosphide, this is the indium arsenide. Gallium phosphide, indium phosphide. So this is the boundary line of the indium gallium phosphide. So gallium phosphide to gallium arsenide, this is the boundary line of the gallium arsenide phosphide. So the indium gallium arsenide phosphide quaternary alloy, okay, is bounded by this boundary line of gallium arsenide phosphide and the boundary line of indium gallium arsenide and the boundary line of indium arsenide phosphide and indium gallium phosphide boundary line. Now, these are dashed line. The reason is because gallium phosphide is an indirect bandgap semiconductor. So if you want to grow indium gallium phosphide, then you expect, okay, a certain composition, there will be an indirect bandgap crossover. So the dashed line represents indirect bandgap. So gallium phosphide and gallium arsenide, this boundary line, okay, if you grow gallium arsenide phosphide, then you expect, okay, a certain composition, there will be an indirect bandgap. So indium gallium arsenide phosphide quaternary alloy, okay, will be in this shaded region. So this will be the quaternary alloy, indium gallium arsenide phosphide quaternary alloy. Okay, if you just look at the boundary line, these are only ternary alloy. Gallium arsenide, indium arsenide point. So if you draw this line, they are basically indium gallium arsenide, okay, ternary alloy. So indium gallium arsenide phosphide is in this shaded region, okay, bounded by these 4 ternary line. So let's say I grow indium gallium arsenide phosphide on indium phosphide substrate. So basically I will look at the lattice constant, okay. This is the lattice constant value. So this is the lattice constant of indium phosphide. Okay. And that value, okay, to be more accurate, is 5.8687. So at this point is 5.8687. And along this vertical line, okay, along this vertical line, okay, that match the indium phosphide. So if I want to grow on indium phosphide, I would have a band gap of indium gallium arsenide phosphide quaternary alloy, okay, of this range, which is this band gap energy, okay, that I can grow on lattice constant of indium phosphide. So lattice match. So any value here I can pick, okay, that will be lattice match to indium phosphide, okay, for a certain composition of X and Y, okay, for a certain composition of X and Y. I do not know the composition, okay, but there is certain composition of X and Y that I can grow such that it will match the lattice constant of indium phosphide. So that is the gap, the range of the gap for quaternary alloy I can grow. So let's say I grow ternary alloy. So ternary aluminum gallium arsenide. Aluminum arsenide is here, gallium arsenide is here. So you see there's the green dashed line here because aluminum arsenide, as we discussed, is indirect band gap. So moving from gallium arsenide to aluminum arsenide has certain composition, okay, of aluminum, there will be a crossover or indirect band gap. So in order to grow aluminum gallium arsenide, I can grow from here, this range, to this range, okay? So it's along this line. But I must find appropriate substrate along in the lattice constant such that I can have lattice match, okay? I can grow aluminum gallium arsenide. Of course, the best will be to grow on gallium arsenide because along here you can see the aluminum arsenide and gallium arsenide. This ternary boundary line is very almost vertical and it match the gallium arsenide lattice constant. So I can grow, okay, aluminum gallium arsenide for certain composition, okay, to have this range of band gap energy. Next, I can grow aluminum arsenide or I can grow aluminum gallium arsenide antimonide because this is aluminum arsenide, this aluminum antimonide, this gallium antimonide, this is gallium arsenide. So with these four endpoint semiconductor, I can form an aluminum gallium arsenide antimonide, which is the green shaded region. So inside this shaded region will be my quaternary alloy, okay, band gap energy. I can pick any of the band gap energy. It corresponds to this vertical axis. Again, this is the ternary boundary line or the ternary alloy material. Aluminum arsenide is indirect band gap. Aluminum antimonide is indirect band gap. So you can see that this is all dashed line. So it's, if you change aluminum composition, it will be always an indirect band gap. Okay. But for the quaternary alloy aluminum gallium arsenide antimonide, okay, it will be bounded by these four boundary lines. So we will inside this gap. So if I pick, let's say I want to grow 1.2 EV of aluminum gallium arsenide, antimonide. So 1.2 EV. So it will be in this green region, so along this horizontal axis, but I need to look for a substrate that have a lattice constant I can grow upon. So probably I'll pick this point. Okay, I grow 1.2 EV of aluminum, gallium arsenide, antimonide. And if you look down, this is the lattice constant of gallium antimonide. So therefore I can grow this quaternary alloy. Or I can grow on indium phosphide substrate. So 1.2 EV. Okay, if you take this as the green region, so I can basically in the green region down here, somewhere here, I can grow on indium phosphide substrate. Okay, of course, the composition will be different for this point and this point. Okay, if you grow on different substrate. Next, I can grow indium gallium arsenide antimonide, and these are the 4 endpoint semiconductor: gallium arsenide, gallium arsenide, gallium arsenide, gallium antimonide, indium arsenide, indium antimonide, indium arsenide. So within the red region, okay, that is my quaternary alloy of indium gallium arsenide antimonide. I can also have the yellow one, okay, from here to here. Anything bounded, okay, inside the yellow region is the indium aluminum arsenide antimonide. Now, of course, you can say that, well, I have a range of band gap I can grow, okay, with such a big region. But however, you have to look for the lattice constant. So let's say I pick this point, but I look at it, there's no appropriate lattice constant that I can grow, okay, for a indium aluminum and arsenide antimonide with a band gap of 0.8 EV. I can't find appropriate lattice constant to grow upon. Okay, remember you want to grow a alloy flame on a lattice constant with lattice match. So that gives you the limitation. So the possibility is, okay, I can grow down here with an aluminum antimonide of a band gap of 0.8 EV. Next, the last one is aluminum gallium indium arsenide. So that is your bounded region again, okay, for aluminum gallium indium arsenide. So let us discuss the question, what is the band gap of the indium gallium arsenide phosphide as a function of X and Y composition? Determine the relationship between X and Y if to be lattice matched to indium phosphide. Determine the value of X such that indium gallium arsenide is lattice matched to indium phosphide. Determine the band gap of indium gallium arsenide. So the material lattice constant and the band gap energy are given to you. So by virtual CRISPR approximation, to calculate the indium gallium arsenide band gap, essentially is basically you look at the endpoint semiconductor, indium phosphide, the subscript is 1 minus X and Y. That will be your weighted factor. So you take it as 1 minus X, Y, times the band gap of indium phosphide. And then indium arsenide, the other endpoint, you have 1 minus X and 1 minus Y. So that will be your factor of 1 minus X and 1 minus Y. And then the band gap of gallium arsenide, you have X and 1 minus Y. So that will be your factor X 1 minus Y. Plus gallium phosphide. So there is X and Y. So multiply by the weighted factor of X and Y. And then you plug in the given value of band gap of indium phosphide, indium arsenide, gallium phosphide, and then you rearrange the term, you would have a equation of the band gap of the alloy of indium gallium arsenide phosphide is a function of X and Y. Now, I want to grow indium gallium arsenide phosphide. Okay. And next is the how to find indium gallium arsenide phosphide, lattice constant. So the band gap itself, you just change to lattice constant. And then you just plug in the lattice constant value. So you just put in the numerical value of all the lattice constant, but just changing the band gap to lattice constant. And you plug in the value. So this will be the equation for the lattice constant. Now I want to grow indium gallium arsenide phosphide. Okay, lattice match to indium phosphide. So this is the equation of the indium gallium arsenide phosphide. And lattice match to indium phosphide, that means that this equation, I equate it to the lattice constant of indium phosphide. So it's equals to, lattice constant of indium phosphide. So the lattice constant of indium phosphide is 5.8687 equals to this equation. Okay, then I can find Y in terms of X. Next, I want to find the composition of indium gallium arsenide lattice match to indium phosphide. Now, if you look at indium gallium arsenide phosphide, how do I make it to become indium gallium arsenide when there's no phosphorus? If there's no phosphorus, that means Y is 0. So Y is 0. So I will have just indium gallium arsenide. And that will be indium gallium arsenide. It just depends on the composition of gallium and indium. So that is when Y equals 0. And this equation itself is derived based on the fact that indium gallium arsenide phosphide is lattice matched to indium phosphide. So when Y equals 0, and we put Y equals 0, then it becomes an indium gallium arsenide for lattice matched to indium phosphide. Then you can find the composition of X. So from here, you put Y equals 0, you solve for X, you get 0.47. And then what is the band gap of indium gallium arsenide at 0.47? You go back to this equation. Y is 0, so you left this part. So just put in X 0.47, you get the band gap of 0.857 eV. So again, if a semiconductor have very large lattice mismatch, that means you grow semiconductor alloy. Okay, the lattice constant of the alloy, okay, is either smaller or bigger than the lattice constant of substrate, okay, and the strain cannot accommodate, okay, the mismatch, then you would introduce defect. So such a defect could be microscopic defect, misfit dislocation, and such a defect especially will propagate from the interface into the film. You'll degrade your quality of the film, and that affect, especially if you want to use the film for light emitting diode, you will reduce the radiative efficiency of the semiconductor. Now, if you look at this graph itself, there's no aluminum phosphide. It should be at this range. So usually people will have another plot of aluminum phosphide down here. Okay, so gallium phosphide all the way to gallium arsenide, which we have seen, gallium phosphide all the way to gallium arsenide, okay, and then to indium phosphide, and then to indium phosphide. So gallium phosphide, indium phosphide. So this is a plot of aluminum phosphide, gallium phosphide, okay, and basically, okay, you can make use of aluminum, gallium, indium phosphide, okay, for a certain composition such that you can find a lattice match to gallium arsenide, okay, and where you can have green, yellow, orange, or even red, okay, emission of the wavelength. So for example, if this is aluminum phosphide, gallium phosphide, this is indium phosphide. So this range itself is aluminum phosphide all the way to indium phosphide. Okay, aluminum phosphide is indirect band gap, indium phosphide is a direct band gap. So there will be a dashed line, there will be a crossover such that aluminum phosphide is the indirect band gap. Okay. Now, if I grow within this region, okay, I don't want to grow around here, which is a lot of indirect band gap. I want to deal with direct band gap. I can pick, okay, any point along here, okay, which is a aluminum, gallium, indium phosphide alloy, and I can grow on gallium arsenide substrate. So depending on the composition of the value, I can change from red to orange to yellow and to green. So that's how we do band gap engineering. Okay. First, you must find an appropriate substrate to grow upon, and then you change the composition. You can change the wavelength of the semiconductor. Now, for this plot, it's a band gap as a function of lattice constant. And we can only say that for certain composition that we grow, you can get a certain band gap energy, okay, and lattice match or lattice constant. Similarly, for this plot, energy gap as a function of lattice constant. Another plot, okay, is a contour plot where you plot the composition as well as the band gap energy. So in this contour plot, okay, at x equals 0, let's say you plot gallium, indium, arsenide, phosphide. So when x equals 0, y is 0, x is 0, y is 0, you have only indium phosphide at this point. And then you can have gallium phosphide where x equals to 1 and then y is 0. So you have gallium phosphide. Okay, and you can have indium arsenide, okay, where x is 0, okay, and y is 1. So that is indium arsenide at this point. And you can have gallium arsenide at this point, where x goes to 1, y is 1. Okay, so this point is 0, 0, okay, 0, 1. This point is 1, 1. Okay, and this point is 0, 1. And this point is 1, 0. Okay, for x goes to 1, y is 0. So these are the composition of x. This is the composition of y. Okay, because the x is on the gallium and the indium, and the phosphorus itself is basically 0. So this is the x range and this is y range. So for certain and this straight line is basically lattice match, okay, to indium phosphide. And these are the contour of the energy gap. Okay. So any line, any point that fall, let's say on this line, is the band gap is 1.58 eV. Any point that fall on this line is 1.74 eV. Any line that fall on this point or on this contour line is 0.947 eV. However, if I have a point at here, that means it fall on this contour line of 0.789 eV and at also intersect at this y straight line. This is basically to say that I can grow in the gallium indium arsenide with composition of X of 0.4 and Y of 0.9, lattice match to indium phosphide substrate. Okay, so that is how a contour plot of the X and Y composition looks like, where you can have X and Y composition. Of course, you need to have measure more contour plot of the band gap so that the separation, okay, will be getting narrower and narrower, and then you can always easier to find the intercept. Okay, and this is basically the line of intercept. Any contour plot that intersect this red line, it will be lattice match to indium phosphide. So again, let's say I grow gallium indium nitride arsenide. Okay, x0 all the way to 0.05 and indium 0 to 0.6. Okay, I did not extend all the way to 1. Okay, it need not extend all the way to 1. Okay, it depends on the desired outcome that you wish to grow the material. So this straight line again, okay, is the lattice match to gallium arsenide. Again, the contour line are the band gap energy of the alloy itself. So if I have this point, okay, so basically the intercept here give me a 0.028 of x, and the y-axis give me a 0.08, and again this is 1 eV, the contour line. So I grow gallium indium nitride arsenide of composition of x 0.028 and y 0.08 with a band gap of 1 eV. Okay, so this is known as the band gap mapping. Okay, as a function of x and y. Now, the next example is indium aluminum gallium arsenide. I will leave this example as an exercise for you, okay, to go through, and the solution is already given to you here. And this is a table of the compositional dependence of the band gap energy in ternary 3-5 semiconductor at room temperature. So these are aluminum indium phosphide alloy. The direct energy gap is given here. The indirect energy gap is given here. So again, the notation should be gamma, gamma, gamma x, and gamma L. Okay, measure respect to the top of the valence band. Okay, we shall stop here, and our next lesson we will discuss about spinodal decomposition, where in which the alloy can separate into distinct phases or formation of coexisting phase.